We begin with a word of prayer. Heavenly Father, we thank you for this day. Again, Lord, I thank you for the students. Just ask you to help us to use this time wisely, just to try to fill any gaps that are missing in lecture, Lord. In your name I pray. Amen. So there's one thing I promised you guys that I should do before I forget, which was the proof that there's a little proposition. I mentioned that this proposition would basically be, like a reasonable test question, which was that if A1, A2, AN are in R M by N, so these are matrices, and then A1 plus A2 plus plus AN IJ is just equal to A1 IJ plus A2 IJ plus AN IJ, and that's for any n in the natural numbers. So I use this in the middle of that somewhat complicated calculation I did at the end of class last time, right? So just, I don't know, some of you have had Math 2, I think most of you, how many have had Math 200? Everybody, anybody had Math 250 instead? All right, so we're trying to stop that, partly because you guys have not seen nearly as much induction as those folks, at least depending on my understanding. I've never taught 250, so I'm not sure. It used to be 250 had a bunch of induction in it, but it's kind of, the course is kind of like transmuted into something different over the years, and at some point we had to stop and go, wait a minute, this should no longer be a prerequisite. And we had a meeting about, I don't know, it was a while ago, and we all voted that it shouldn't be a prerequisite, and it's still not on the books. So, people are still getting in here with just 250. I think you can survive. I don't think it's like a deal breaker. It's just for the sake of students, we're trying to route everybody through 200. It's better. But anyway, what's done is done. So, yeah. But that's part of the reason I'm covering this in here. Here's the proof. So we're going to use proof by mathematical induction on n, right? So n equals 1 is essentially just notation, right? Like A1ij is equal to A1 ij. Yep. I mean, there's really nothing much to say there. That's just essentially notation. N equals 2 is the definition, right? We have A1 plus A2 ij. Why is that equal to A1 ij plus A2 ij? Well, this is the very definition, right, of matrix addition. So if we're doing an induction proof, now what we do is we suppose that A1 plus A2 plus plus AN ij is equal to A1 ij plus A2 ij plus plus AN ij for some n in the natural numbers, n greater than or equal to, let's say, 2. Since we already know it's true for 1 and 2, why don't we just focus on the part we care about? I mean, I guess you could put 3 even there if you wanted, but it doesn't really matter. And what should we consider? How about A1 plus A2 plus plus AN plus 1, right? That was, yeah. And so what we do is simply use the associativity of matrix addition, which if you want to get picky, there's a proposition there I need to prove too. Well, let's see here. Let's look at it this way. This is all a matrix A, right? So what we have here is A plus AN plus 1 IJ. Does that make sense? And then we can use the definition. This is AIJ plus AN plus 1 IJ, using the definition of matrix addition. And then what's my next step? Well, it's the ijth component of that, right? So by the induction hypothesis, that's A1ij plus A2ij plus da-da-da plus ANij. So by the induction hypothesis, I can say that's A1ij plus da-da-da plus ANij plus AN plus 1 ij by induction hypothesis. Yeah.
So when you're calling A1 plus A2 all the way through plus AN, you're just calling that A so that to read more easily. That's not a definition or anything.
I mean, I'm defining that to be A, yeah. But, I mean, that step is, okay, so I'm fine with you guys going directly to, like another way to do this, instead of, all right, you got, everybody see this? Let me, actually, let me just put it off to the side over here, an alternate path to proving this. Like, suppose you don't want to invent that AIJ. Suppose you don't want to invent the A. Often I don't invent the A, I just go straight to, what's the logic here? So, I mean, you could just do, there's another notation for the same thing, would be A1 plus A2 plus AN IJ plus AN plus 1 IJ by definition of matrix addition applied to A1 plus A2 plus AN and AN plus 1. I mean, that's an alternate way of expressing that step without inventing the A. That would also be fine. I invented the A because it helps, like, starting students sometimes to invent a letter to just to express what we're actually using in terms of the definition carefully. But in any event, whatever notational path you choose, we get to showing that the n plus 1, you know, the ijth component of the sum of n plus 1 of these is the sum of the components respectively, right? Hence, the proposition is true by mathematical induction. Thus, n implies n plus 1. Well, let me not say that. I need to give this, let me call this whole, I really should have done this a while ago. Let me call this thing star. All right. So, to be utterly precise. Whoa, yeah. That does not make sense. Well, thus, star true for n implies star true for n plus 1. Thus, I mean, therefore, star true for all n in the natural numbers by proof by mathematical induction. But in a pinch, I'll just write, consequently, the proposition is true by induction on n, if I haven't labeled star. But to be more precise, that's good. Yeah. I mean, I'm probably not going to take a point off your proof on the test if you have done this part carefully. You know, you're just missing. I mean, I want a conclusion, but the conclusion doesn't have to be quite that verbose either. Yeah.
For our proofs, do you want to write like by definition?
Yeah.
Matrix addition of? Okay.
Yeah. That is true. It's just generically speaking, you want to convince me that you know what you're doing, right? So I show a lot of proofs, and the notes are full of proofs, and those kind of give you good models for what I'm looking for. Yeah. I think inadvertently we have shown that I mean, there's other things going on here, right? I'm assuming that associativity of addition in the ring implies generalized associativity in the ring. Like, I've defined associativity in terms of three things, right? I'm saying that that equally well extends to n things. To actually prove that's kind of a pain. I'm just going to assume it, okay? You guys didn't even notice, but I used it. I used it here. How have I mean, I used it even here, this generalized associativity I've used, because you notice that I haven't told you whether I'm adding this one, then adding all these, or if I'm adding all these and then adding this one, or in what order I'm doing the addition, you know. I didn't write parentheses, you can't tell, right? So I'm assuming it doesn't matter which order you add them in. That's generalized. Well, that's associativity extended to more than three objects, but. All right, let me shut up. So anyway, there it is, yeah.
Is there a reason why we had to do n equals 1 and n equals 2?
Not really. In fact, you could have just done n equals 1, assumed it's true for n, greater than or equal to 2, and done the rest. But as a point of habit, I usually check the first couple cases just to make sure I'm not tricking myself. You know, there's these pathological examples where it fails at like 3 or something, and you can. Did you guys look at some of those in 200 where you can get trapped? I vaguely remember conversations with Dr. Joseph looking for such examples. So, I mean, a way to create an example which is false is you just take an equation which is not true. I mean, something like n squared equals to n squared plus 3, you know, or something like that. Assume it's true for n. You can prove it's true for n plus 1. but it's not true ever for any of the base cases. So something like that. Neglecting base cases can get you in trouble. But yeah, I don't know. It's not especially interesting. Okay. Any other questions? I think that was pretty much all I had in terms of what I left out last time. If you'd like, I can just show you a slew of matrix multiplications. Would that be helpful? Yeah. So example 1, let's try something like, we'll start out with the friendly case, 3, 4, 0, 1, and I'll start out with 1, 2. All right, so to multiply these two, we get 3 times 1, 4 times 2, 0 times 1, 1 times 2, right? Which is, what, 3 plus 8, 11, and 2. Now that makes sense, right? Because we've got a 2 by 2 times a 2 by 1, and the output is 2 by 1. Do another one of these. Same matrix, 3, 4, 0, 1. And this time let's do 0, 1. What should that tell me? What should that be? So if I call this matrix A, right? This is what we called E2 last class, right? So I claimed you can prove, and I'll do that today at some point once we've done a bunch of numerical examples, that AE2 should just be column 2 of A, right? And you can see, if you multiply this out by the definition, really the dot product formula is what I tend to use for numerical ones. That's 3 times 0 plus 4 times 1, which is 4. 0 times 0 plus 1 times 1, which is 1. Indeed, that is column 2 of A. Now, there's more we can look at. If we look at 3, 4, 0, 1, right, times 1, 2, 0, 1, what do we get? Now we got a 2 by 2 matrix times a 2 by 2 matrix. We should get another 2 by 2 matrix. The product of square matrices is another square matrix of the same size. But I can tell you without looking that this is 11, 2, 4, 1. Did you get that? The reason for that is a proposition. See if I call this, let's call this vector up here, I don't know, x. See what this is equal to. This is equal to AX concatenated, glued together with AE2. See, this over here is A times the matrix X glued together with E2. This is the column by column matrix multiplication rule. Generally speaking, if you have like A times a matrix with columns B1, B2, Bn, you can multiply it column by column in the sense that this just works out to AB1, AB2, ABN.
That's just the definition of matrix multiplication?
No, that's a proposition. You can prove that.
Can you prove that using the definition?
Yeah. In fact, that is one of your homeworks. So, okay, so moving along here, example 2. Might be good to look at something like 1, 2, 3 times the matrix 1, 1, 1, 0, 0, 0, and 3, 4, 5. How's that work? Does that even make sense? This is a row vector. It's what? It's a 1 by 3, right? This is a square matrix again, which is a 3 rows by 3 columns. It's square. So yeah, that should make sense. We should get a what? A row vector out, right? So how do we do that one? I'll use some color coding. Basically take the dot product of this one with that, right? And that gives me 1 plus 2 plus 3. Then I take the dot product of the second column with that. That gives me 0. Then I take the dot product of the third column with that row. I get 3 plus 8 plus 15. So what's that work out to? 6, 0, and 26. So we can multiply by a row on the left of a square matrix if it's the right size row. Here, let me do one that, how about this? What if I try to multiply 1, 2, 3, 4 times the row vector 6, 7? I've just been doing examples that make sense up to this point. Look at this one. Here we've got a 2 by 2. We're trying to multiply it by a 1 by 2. This is not defined, right? If you try to put this in your TI calculator, at least back in the day, it used to say dimension mismatch or something. I don't know what it says now, but it shouldn't do it anyway. Now, it's one of the problems with Wolfram Alpha is sometimes you can put stuff like this in and it'll invent a meaning for you. But no, it's no good. Technical phrase. All right. Example 4. Let's see here. What happens if we try to do a, how about this? What if we do well, let me do something a little bit more. I was about to do something. 1, 2, 3. We'll make it a row vector times 0, 1, 1. That's a what? That's a 1 by 3 times a 3 by 1. What should the answer be? A 1 by 1, right? So in fact, in this case, that just reduces to just plain old dot product of the vectors, right? I mean, it's so it's 0 plus 2 plus 3. The answer is just 5. And in the case we have a 1 by 1, we just drop the brackets, right? I mean, if you wanted to be obnoxious and a purist, you could say there's 1 by 1 matrices, they have brackets. The ones that are not matrices, they don't have brackets, and we're going to distinguish between these things. I've never seen anyone reach that level of stupidness, but I could see myself doing it in certain contexts. But anyway, 5. What happens if we just reverse the order, though? What would happen if I do 0, 1, 1 times 1, 2, 3? Would that make sense? Yeah, we get a 3 by 3, see, because that would be a 3 by 1 times a 1 by 3. And here is where the definition starts to, I mean, I wrote the definition in terms of dot products, but this will catch you guys on a test if you haven't seen it before. I do try to make sure that we have a robust set of examples in the homework and everything, but, you know. I mean, the definition I wrote is overarching, but it has to be only with, you know, you have to understand that, like I was saying in class, there are when either one of the sort of exterior dimensions, the m or the n, was 1, an index disappears, or both indices disappear. You have to be careful how to interpret that. But anyway, this one, how does that work? Well, so this spot right here, it's 0 dot product with 1, so to speak. I mean, the dot product of one-dimensional vectors is just multiplication. I mean, so we just multiply those numbers. And then we get 1 times 1, 1 times 1. But let me be less weird and just write the answer. So what we get is 0, 1, 1. This one here, we get 2. Oh, I'm sorry, I can't do math. 2 times 0 is 0, right? So 2 times 1, 2. 2 times 1, 2. And then over here we get 0, 3, and 3. So you can build matrices from the product of rows and columns in the opposite order. A column times a row gives us a matrix, as long as they're the same size. How about this? What if we do 1, 0, 0 times 0, 1, 0? What's that give us? So if you figured this out yet, it's pretty simple. We just do scalar multiples of the column to get the column of the matrix, right? I mean, so I get 0, 0, 0. I get 1, 0, 0. And I get 0, 0, 0. This example is actually a little bit preachy in the sense that what I'm showing you is part of a more general pattern. Can you guys tell me what is this? Oh, you're getting ahead of me. You're telling me the interesting part. This is E1, 2. Very good, right? That's one of those matrix units we defined yesterday. We said we can build any matrix from that. And the other side, well, this is a standard. This is E1, right? Now, what's this here? E2. Almost right, but not quite right because it's a row vector, so we have to transpose. So this is E2 transpose. So what this example shows you is that E1, 2, we can build E1, 2 from the standard basis, just the same, if you like, the square E1, 2. I mean, E1, 2 could be rectangular. I'll do that in a second here, but did you see it? Look, we can generalize this. If you have Eij, the square Eij, you can build it from Ei times Ej transpose, just the same. That's actually true. Here's a proof. So how would we prove that that's true? I mean, a common method of proof in courses you've had up to this point would be something like, I show you this example, then I say, you could do this for any choice of I and j, and that's the proof, right? But that's not really a proof, right? That's a plausibility argument. Proof would be something like this. Eij, well, we want to show that these two things are equal, right? So what I'd like to show is that the k-elf component of both sides is matching. So if I look at the k-elf component of Ei times Ej transpose, look at the k-elf component of that. What's that going to be? You got to think about this. This is like the k-elf component of the product of two matrices, right? So this is going to be the sum I equals 1 to n of E sub I. I'll put some parentheses in here for us. K I. Ooh, now this is I've just committed a cardinal sin of index manipulation. I've used I here. I'm about to use I. I'm going to fix it. But I should not use I here as an index of summation because I have also put it over here as a label. This label is fixed and arbitrary. I can't then also use it as a summation index. I need to come up with another letter. How about A? A equals 1 to n. So that's the A. I'll put that here. And then I have Ej, excuse me, transpose AL. What I'm doing there, guys, is I'm using the definition of matrix multiplication. I'll write it over here. Remember that? AB. I'll write it in terms of K and L. That would be the sum A equals 1 to n of A, K, A, B, A, L. Sorry, I seem to have used big A and little a. These things will happen. If I could write more Chinese characters, we'd have a better alphabet to work with, but kind of unlimited. But then you guys wouldn't be able to write it, so we'd be back where we started. It's kind of like when I was in physics and I was taking notes in this one lecture. And I thought, I'm keeping up with class. And then all of a sudden, about 20 minutes into it, I realized that there was an uppercase K. There was a lowercase k. And there was a kappa. And I wasn't sure which one of each one of those things were. And P is awful. Physicists use P in like 30 different ways, sometimes redundantly. Anyway, but this is just the definition of matrix multiplication in this context. And what we define this to be what? This is Kronecker delta. Oh. Oh. No, I can't write that. I've tricked myself. No, I shouldn't write that, should I? What would that even mean, EIKA? EI is what? It's a column vector, right? It's just got a single index. So what I should write here is just this. No, that's still wrong. I think I chose poorly. Curses. I'm sorry, you guys. I have managed to work myself into a corner, literally. That must be, this must mean, oh, well, we saw it in the example, right? There was no sum. To figure out the kth component, what did we do? We just multiplied the kth component of the left thing by the lth component of the right thing, right? And the same is true over here. If I just read my definition correctly, I should just have, there's no sum. So sorry, guys. It's good we do this, though. I'll show you another way to understand this later. EI, this is the kth component of that times the lth component of this guy. That's how the definition of matrix multiplication shakes out for a column times a row. Yeah, it's funny. So I really need to, the next edition of my notes, what I'll do is I'll put in all these different cases. I'm sorry, I'm not there yet. I'm still learning how to teach this stuff, but it seems to me that there are exceptional cases. Like, so we're looking at so it kind of makes sense. Here's the exception. The places where the index rules get weird is, we've got m times p by n, right? So last class, I kind of talked about when you have something like 1 by p by n, right? And then I realized, well, it's also weird if you have m by p by 1, right? The usual index formula doesn't quite, it requires some interpretation. And we also realized, well, if you've got 1 by p by 1, that's also a kind of special case for the notation. And I think we've seen, let's see here, this is a 1 by 1. This would be example what? Example 4 is like this case, right? Did we have something like this here, where our output is m by 1? M by 1 is what? Column. This is actually pretty common. This is something like matrix column multiplication, right? And this is what? This is, row matrix, row times matrix. So row times matrix gives row, right? Matrix times column gives column, right? And row times column equals number. That's the pattern, right? But there's another weird case that hadn't even occurred to me to think of as a weird case, and that's the one we're just discovering right now in terms of thinking of it as a weird case, which is m by 1 by 1 by n. And the weirdness of this case is that in the definition, the thing that goes away is what? The sum. And of course, I should have realized that, because It's the matching of the column of the left factor and the number of rows of the right factor in the multiplication that frames the summation here, right? This is ranging over whatever p ranges over. When p ranges over one value, the summation just becomes, it's gone, right? It's just a product, which is why I wrote this here and there's no sum, okay? And then it's almost trivial. So this is delta ik, and this is what? It's kind of silly, but it's also delta JL. The question is, what's the Lth component? What's the Lth component of the transpose of the jth standard basis? Well, it's either 0 if j is equal to L, or it's 1 other. It's 1 if j is equal to L, it's 0 otherwise. So that's Kronecker delta JL, just the same. And this, of course, is nothing more than the k-Lth component of Eij. So you've shown it for arbitrary KL. Therefore, Eij is equal to Ei times Ej transpose. I think it would be healthy for you guys to see me just write down index notation for those cases. Yeah? This one comes up the most if I have like a times x. Oh, I'm sorry, let me guys, everybody fine on this? Yeah.
Can you just explain the going from the e's to the deltas again?
From here to here?
Yeah.
Okay, so what does EIK mean? This is the kth component of EI. But actually, last class, I defined that to be Kronecker delta IK. So going from here to here is actually, this to this is definition of EI. EI is the standard basis. It has a 1. It has a 1 in the ith spot, and it has a 0 everywhere else. So if I ask what's the kth component of that, it's 0 when I is not equal to k, and it's 1 when I is equal to k. That is the Kronecker delta. That's what this means. Kronecker delta IK, 1 for I equals to k, 0 for I not equal to k.
So why do we use delta and just saying kth element of EI? Is that just to help show that, or?
Well, if I didn't use delta, I'd have to write out 4 cases.
Oh, that's right.
Yeah.
Okay.
Yeah, delta is a way of not writing this. It's a nice notation for expressing multiple cases at once. Now, let's talk more about the deltas and all that before I fished into this. We'll get back to that soon enough. How about this? So you guys are not quite comfortable with the I's yet. I get it. How about EI.EJ? What would that mean? Talking about dot product for a second. So this is what? This is 0, 0, 1, zeros, 0, dotted with 0, 0, 1, 0, 0. Let me be a little bit more clear. What do I mean? This is in the ith spot, and this is in the jth spot. So what's the dot product of EI and EJ? It's 1. Well, it looks like that, but it's not necessary. I mean, it depends on what I and j are, right? If I and j are both 1, it's 1, right? If I is 1 and j is 2, it's 0.
So it'd be
written in no particular order. I'm sorry. But here's E1.E2 in 3 dimensions, E1.E1, E1.E3. First one's 0. Yep. Third one's 0.
So it's ij.
Yeah. So in short, this is Kronecker delta ij. Now the dot product of 2 column vectors we can also express as this, aka EI. To get a number from 2 column vectors, what do I have to do? Where does the transpose go, on the left or the right one? I want it to be a 1 by 1. I want it to be like that, right? So what is a column vector? It's a what? It's an n by 1, right? So the one on the left has to have a transpose. Yeah, so this is in fact equal to EI dot EJ. But anyway, there's another way we can look at it. EI transpose times EJ, right? This is Kronecker delta IJ.
But at the top we said EI times EJ equals the Kronecker delta IJ.
Yep.
Why is one of the transpose and it equal to the same thing?
One of the
When
transpose.
you boxed. So the top is just EI.
Oh, that's because this is also equal to EI dot EJ. The question is, do you want to talk about dot products? See dot product. This is matrix multiplication. Matrix multiplication is hard to see in the sense that we use juxtaposition. We use things being next to each other to denote matrix multiplication, whereas, well, the dot product is so named. Dot, big old dot, you know. Not to be confused with the smaller dot I sometimes write for just plain old multiplication or scalar multiplication of a matrix, right? Those are not dot products. Those are something else. Does that make sense? Okay. Hey, let's get back to another numerical example. You know, I can blather on about these matrix units and the EIJs, and the point of these is they'll allow us to prove things that if we were to use the more clumsy ... writing big boxes of numbers notation, it would be very difficult to actually write them out and be careful. And sometimes we might not just be able to see things. But anyway, it's more than just that. It's you know, but it is a new way of thinking. I know. What example am I on? Example 6. How about this? What if I have 0, 1, 0, and I'll take this matrix 1, 2, 3, 4, 5, 6, 7, 8, 9, and then how about we do 0, 0, 1. So what? Matrix multiplication is associative, by the way. All right. So it doesn't matter which one I multiply first. Which one? I think personally, I like to multiply the column first because that's what I'm most familiar with. I think about matrix column multiplication a lot. I think about row matrix multiplication not nearly as much, personally. So what do we get? By the way, you guys, you shouldn't actually have to work out that multiplication. You should start to think about using the theorem that I mentioned earlier today, which was what? I've erased it. I haven't proved this in class yet, have I? Theorem A, oh, this marker's awful. AEI is equal to column I of A. I don't think I proved that in class yet, did I? I think I stated it, but I haven't proved it. Yeah. But using that here, this is, think of this as A, right? This is what? This is E3. So what happens when you multiply these? We just get what?
The column of A.
Yeah, which column? The
Or no, the
third column, right. So this is 3, 6, 9. I don't actually need to do those 3 dot products. I can just use this result. This is a result worth knowing. I expect you to know it. Okay. I mean, knowing that result's very labor saving. Yeah. And then what's that give us? Actually, there's another result, which is that if I take EI transpose times a matrix, let's say B, that's equal to rho I of B. So what I mean, this is E2, right, times B. What's it going to do? Yep, it picks out 6. What's the significance of 6 here? Which component of A is it?
2, 3.
Yeah, 2, 3. Yeah, so E23, A23 is apparently E2 transpose A E3. This is yet another theorem. So theorem AIJ is equal to EI transpose A EJ. If you want to, I'm assuming A is square at the moment. Admittedly, if A was rectangular, I'd need to use a different standard basis for the different size because it'd be different sized. Let me show you that in an example. I'll probably prove that tomorrow, so I won't do it at the moment, I guess. But I mean, if you think about it, it makes sense, right? I mean, multiplication on this side picks off the jth column, right? And then multiplying on the other side picks out the ith component of the jth column, which is exactly what we mean by AIJ. So it's I don't know, it's kind of nice. Oh, here, let's put these things together, then I'll really stop talking about stuff. What if I was, let's look at this proof that I did over there in a different way. Let's look at EIJ, let's calculate. I claimed that EIJ was equal to what? EI transpose? No, EI times EJ transpose, wasn't it? I can't remember. I guess I could just count. This is n by 1, that's what, yeah, okay, we're good. You got to be careful which side you put the transpose on really matters, right? One is a matrix, the other is a number. Very different things. But how about this? If I wanted to calculate the kth component of this, one way I could do it is in terms of this theorem, right? I could say, well, that's really EK transpose, EIJ, right? EL. But we know by definition that that's what? Kronecker delta, IK, Kronecker delta, JL. Sorry, I'm burying the lead here. What I really want to do is EI, EJ transpose. The question is, why is that equal to the thing above, right? To calculate the kth component of this, we have EK transpose, EI, EJ transpose, EL. And that's really nice because then you can just go back to the fundamental thing, which is what? that like EA dot EB is equal to delta AB, right? But in terms of matrix multiplication, what is that? The transpose goes where? On the left factor, right? So this is EA transpose EB equals to delta AB. So I can use this to simplify that, right? So I got to be careful. I'm looking for when the transpose is on the left. But look at that. That happens 2 times here, right? This one and that one. This is just what? Delta KI delta JL. And by the way, this is the Kronecker delta is symmetric in the indices. Like this is equal to Kronecker delta IK, Kronecker delta JL, right? Which is of course equal to EIJ KL. So there is another proof that you can build the square matrix unit by a product of the standard basis and its transpose in the appropriate order. So which is better, using components or kind of using this transpose multiplication of standard basis units technology? I don't think you can say one's better than the other. They're just 2 different ways of approaching it. These are tools in our toolbox. Certainly, this idea and the other one I said is really important. Do you guys have questions? Yeah.
So you switched the order. I may have missed most of the notes, but you switched the order of the K and the I.
Yeah.
Stop any of the Kronecker delta. Why are you allowed to do that?
Because the definition of Kronecker delta is that Kronecker delta IK is 1 if I is equal to K, or 0 if I is not equal to K, and the role of K and I is symmetric.
Order doesn't matter.
No.
You're not referring to the quarter. Okay.
No, doesn't matter. Here, let me actually. Oh, that red marker. Okay, so guys, if we have a rectangular matrix, how would that be different? So suppose we have, what if we have like A equals to 1, 2, 3, 4, 5, 6, 7, 8. In this case, I could do things like A times 0, 1, 0, 0, right? And what would that be equal to? 2, 6, right? Because we're looking at A times E2. On the flip side, if I did, 1, 0, 0, 0 times A, what would that be? No, it's not defined. See, this is a trap. This is a 1 by 4, and that's a 2 by 4, right? So this is not allowed. What we have to do is 1, 0 times A. So this is a 1 by 2 times 2 by 4. So that should give us a 1 by 4 row matrix multiplication. And that will pick out what maybe what you said. Yeah, 1, 2, 3, 4. So this box thing over here, it's not quite true. Like, to be a little bit more pedantic about this, I really should maybe, I don't know, put a bar on this guy and say that if A is an element of Rm by n, right? So to make the multiplication make sense, I need like 1 by m times m by n times n by 1, right? Which means that the EI bar has to be an element of what, whereas EJ has to be an element of what, to make that multiplication make sense? M, right? EI bar is an element of Rm, whereas EJ is an element of Rn, right? So just like my numerical example over here, I can multiply this 2 by 4 matrix by 4 vectors on this side, but I can only multiply it by, two vectors, row vectors of length 2 on the left side. Okay. So if you and so like I don't know, it's kind of bad form, right? To use the same notation for the 2-dimensional thing and the 4-dimensional thing at the same time. So in a situation like that, I might put a bar on one of them to indicate it has a different dimension, or I might use a different letter even for the standard basis if I get pushed to that. But I try to just use EI for the standard basis when there's no ambiguity. Okay. So there's that nuance. So you guys have any questions about anything going forward? Or? Yep. Oh no. I thought my computer's plugged in. My computer turned itself off in the time we have been here. All right, that's it. I'm buying a new battery. Yes, I'll take your. Can somebody pass Emma's up for me? Thank you. Okay. So number 3, you're supposed to calculate I times AB and also AB times I, right? So I mean, all you got to do is to calculate AB times 1, 0, 0, 1. I mean, this is what I is given to be there, right? So whatever that is, And then this, on the other hand, keep in mind that we use the hidden column notation, right? So A comma B is actually a sneaky notation for AB. So that's probably what you're asking me about, because I'm pretty sure you can. Yeah, I gathered that you probably can do. So this is actually what's meant by IAB. Yeah. Other questions? Yeah.
If it says A is like part of R, and instead of saying M by N, it just says M or just says N, does that mean it's 1 by M or M by 1?
It's a column vector by default in here, so it's M by 1. Yeah.
Is that n by 1 or 1 by n?
Notice that the transpose is not on the lower statements.
Okay,
Yeah.
makes sense.
But the thing that's multiplying inside the box would be a 1 by M, because it's the transpose of an M by 1.
So both of the Rn and Rn down there are both column vectors?
Yes. But you notice that that's not what appears in the theorem. That's the transpose, which makes it into a row, right? Transpose takes us from the world of columns to the world of rows in some sense, yeah.